Hello, this is video 14. How about 1.4e? We're not in chapter 14. There is no chapter 14. Continuity of different function types. Okay, so we started to see this the last time in video 1.4d. The following functions are continuous on their domains, and that way we don't have to check it every real number. We happen to know these, and then we just check the exceptions. So, polynomial functions are continuous on their domain, which is all real numbers. Rational functions are continuous on their domain, which is all real numbers except those x values which make the denominator equal to 0, and there may be none. Radical functions, their domain is all real numbers except those which make the radicand negative when the root index is even. If the root index is odd, the domain is all real numbers. Domains of the trig functions are cosine and cosine, all real numbers. Tan and secant, because they're over cosine. We talked about that in the last video, at all reals except for the odd pi's over 2. Cotan and cosecant, all reals except for the integer multiples of pi. So numbers 31 through 34 are once again going to say discuss the continuity, but this time it's discuss the continuity of the function on the given closed interval. So they're going to give you the function, not the graph, and you don't want to have to graph it. And they're going to give you a closed interval, and the question is it continuous on this closed interval? So remember, to be continuous on a closed interval, it has to be continuous everywhere between -3 and 3, continuous from the right at -3, and from the left at 3. But the easiest way to look at this is to look at it as a type of function and say, oh, this is a radical function. Since it is a square root, it's continuous at every number on its domain. And that domain is all of the numbers that make the radicand greater than or equal to 0. So what happens is you take the radicand, the quantity inside the radical, make it greater than or equal to 0. Now, the way to solve a quadratic inequality is to make sure one side is 0. Factor the left side. You know that -3 and 3 would make it equal to 0, and therefore the possible regions or intervals where it could be positive or negative are to the left of -3, between -3 and 3, greater than 3. So if I pick a number such as 0, which happens to be between -3 and 3, and plug it in, I will get a positive. Since these exponents are both odd on these factors, the signs will alternate. So once I know that I have a positive here, that means I have a negative here and a negative here. We want the radicand to be positive. That only happens here. It can be 0, so we fill in the dots. So it's continuous on its domain, which happens to be -3 to 3. So the question was, is it continuous on the closed interval -3 to 3? The answer is yes. Now, the next questions I'm going to ask, which they don't ask, is now that you know it's continuous on the closed interval from -3 to 3, my question, is it continuous on the closed interval between -2 and 1? Well, the answer is yes, because all of these numbers between -2 and -1, including -2 and 1, are on this interval. Is it continuous on the interval from -4 to 2? The answer to that one is no, because it is not continuous to the left of -3, which is what -4 is. Number 34, here's the question. Is it continuous on this closed interval? If you factor it, it's a rational function. The answer will be no, because it's a rational function continuous on its interval, which is whatever makes the denominator not equal to 0, which is -infinity to -2, union -2 to 2. There is no closed bracket. You cannot have a denominator of 0, because then the function wouldn't exist there, so it wouldn't be continuous there. So sure enough, it is not continuous on that closed interval. Had this been an open interval, you would have been fine, but it's a closed interval. So the answer is no. Number 40, same question, another rational function. This time, though, it turns out that the domain is all real numbers, because there is no real number which will make the denominator equal to 0. So you have to state it, and you're going to have to state it this way. And let me emphasize that, although this is not going to be very straight. Let's see if it'll do this for me. Oh, that didn't work at all, did it? Hey, maybe if I just move it up, we'll see. Okay, no, I don't like it. Okay, so what we have is you need to tell me the type of function. you need to say the words, therefore continuous on its domain, and you need to tell me what that domain is. So, since it's continuous on the interval from negative infinity to infinity, the question was, I think, we look for discontinuities, and there are none. Here's a trig function. It's cosine, so remember, it's a trig function continuous on its domain. Cosine, the domain's all real numbers, so it's continuous from negative infinity to infinity. And I don't know why this is here. And therefore, there are no discontinuities. 44 is another rational function. Again, we'll factor. The domain of a rational function is all real numbers except the ones that make the denominator equal to 0. So since the denominator can't be 0, x cannot be plus or minus 1. Do be careful you don't go from x squared does not equal 1 to x does not equal 1. Don't forget the plus or minus. So again, you tell me the type of function. You tell me it's continuous on its domain, and you tell me what its domain is, which is all real numbers. You can write it this way or this way. So, this function is therefore discontinuous at x equals negative 1 and at x equals 1. Now, by the way, the word essential means it's not removable. I wrote that down here. So, they'll ask you if it's a removable or a non-removable, or they'll say is it removable or an essential discontinuity. Well, you can easily go back here and realize there was no common factor in the numerator and denominator, so there's no point discontinuity, so they are both essential. They are not removable. If you were asked to justify that, to be removable, the limit as x approaches that number from both sides would have to exist and equal the same number. But in both cases, because of the vertical asymptotes created by these denominators, the limit as x approaches each of these numbers from either side does not exist. Okay, so here's another example. If the x minus 2's, here the x minus 2's cancel, that'll cause a point discontinuity, whereas this denominator factor will cause a vertical asymptote. So the point discontinuity will be removable, and you could remove it by setting the x equals 2 and y equals 1/7, which is what you get when you plug 2 into here. Okay, but the other discontinuity at negative 5 is essential or non-removable because that factor doesn't occur in the numerator. And that's the end of video 1.4e.